Welcome to Zebra Aurora Vision Studio. In this tutorial, we'll take a closer look at the Detect Anomalies tool available in Zebra Aurora Deep Learning. We'll learn how to use it effectively, train deep learning models, as well as go through the process of building a sample application. The Detect Anomalies, or DA in short, is one of the deep learning-based tools available in Zebra Aurora Deep Learning add-on. It is used to locate anomalies from the learned pattern that are present in the entire image. Contrary to other tools, Detect Anomalies features a semi-supervised training mode, which means that we don't mark defects manually, but classify the good and bad samples instead. The training is also considerably faster compared to other supervised tools. This greatly reduces the time needed for model prototyping and thus reduces time, cost, and effort needed for testing and deploying your project. In this tutorial, we'll build a simple application using Detect Anomalies tool, performing a quality check of plastic electrical connectors. Our model will analyze the image and show us all anomalies found within the object. As you can see, these can be some minor defects as well as the big ones. To perform this task, we have to choose the right tool for the job. The toolbox offers two different Detect Anomalies tools numbered 1 and 2. We'll be using the second one here because we're inspecting a complex object positioned and illuminated in a stable and constant manner. If you want to learn more on how to pick the correct Detect Anomalies tool, please refer to our Aurora Deep Learning documentation. Let's add all the needed filters now and make the connections between them. If you would like to learn more about image acquisition or adding and connecting filters, please check our other tutorials or technical documentation. Okay, we're ready to jump to the Deep Learning editor now. Let's pick a model directory that we're going to work with. The training workflow is similar to our other deep learning tools. We add and classify the images, tweak the training parameters. Next, we set up regions of interest, train the model, and check the results. Let's add some images now from our training dataset. As you can see, we've got both training and test dataset prepared. When training a Detect Anomalies model, we want to use mostly good samples. This way, the model learns what the good product is and will be able to detect any deviations from this pattern. Here, our training dataset contains only good samples. However, we usually should also include some bad samples in our training dataset. These images will not be used in training, but will help in calculating the correct threshold as well as the F1 value. The most crucial step, though, is setting a class for every image. We do it by clicking the question mark icon next to the image. Each image can be classified as either good or bad. We can either mark the images one by one, for example, if the training set contains some bad samples. Alternatively, we can select all images and classify them with one click. Let's do it this way, since we've got only good samples in our dataset. We can now proceed to setting training parameters. We won't be getting into a lot of details here, so if you'd like to learn more, please refer to our documentation. First and foremost, we need to select the network type. We've got two options here, single class and golden template. Since our object has some complex details, we'll be using the golden template here. Single class is simpler and faster, but it works best with less complex objects. Max translation defines the maximal position change tolerance. We'll leave it at default. Model complexity can improve model effectiveness, especially for complex objects. Our object is fairly simple though, so we can try reducing it a bit. As you can see, this saved us a lot of memory, and it will also reduce model inference time. Texture mode is dedicated for detecting texture defects. It has no use in our case, since we're looking for a different type of defects. We'll leave it at default false. To further improve inference time, we can try adding some downsampling. Let's set it at 1 for now. Please note that you can always preview such changes by toggling the pre-processing option. As for the augmentations, we'll leave most at default. We'll just add some relative translation, since object positioning is changing slightly, as well as adjust the minimum and maximum scale by a bit. Seeing that we're dealing with objects with fairly equal positioning and illumination, there is no need to introduce other augmentation parameters. This could have a negative impact on the model and final results. We're ready to train our model now. Before starting the training, however, we need to turn the deep learning service on. When the service is running, the red indicator light in the left corner will turn green. And if we want to turn the service off, we can do so by right-clicking its icon in the system tray. The service is up and running. Let's start the training. Please note how fast the training is compared to some other tools. When we run it for the first time, it usually takes a bit longer to complete, but retraining a model is much faster and often needs just a couple of seconds. Our model is ready to go. We can proceed to analyzing the results now. As we can see, the editor has calculated the threshold levels and F1 values automatically. There's also the score value next to each image in the training dataset. Let's proceed to checking the training results. We could, of course, close the editor and work in the main program window. This time, however, we'll add the test set directly to the editor and evaluate it here. Adding the images will automatically select them in the editor too, but since we have the model trained already, we will be asked if we would like to classify the images automatically. Let's test this feature instead of classifying the images manually. Please note that the new images are still marked as training set. Let's change it to the test set in case we would like to retrain our model. Okay, let's check if our model was able to detect all anomalies in new images. The areas considered as anomalies will be shown using a heat map. This looks really good, especially that the results came almost out of the box. We can always turn the heat map off to show the defect area. Let's check the rest of the results. As we can see, the model is able to identify both large and obvious defects as well as the small ones. We're ready to save the model and go back to our program now. Let's iterate our program and check the results in the main preview window. Our test set will be acquired from a film strip dataset we created earlier. Before iterating your program, please remember to close the deep learning service. You can do it by right-clicking its icon in the system tray. We forgot to add the heat map to the preview. Let's do it now. As we can see, all results are displayed correctly. In the last part of this tutorial, we would like to teach you how to work with the Visualize Heatmap filter. This tool gives us some greater control over how heatmaps are displayed. Let's add the filter now and make all the connections. Instead of previewing the old image and the heat map, we'll just drop the out image output into the preview and remove all other data sources. Let's iterate our program and see the results. As we can see, the whole image turned green. This indicates the area with no anomalies, but it is not necessarily the way we would like to preview our data. We can fix it easily by changing the in-threshold parameter. This looks way better now. This filter also allows us to change the color palette used for heatmap preview. Let's see how it works. There are quite a few palette options available to choose from, which should suit different needs and projects. This concludes our tutorial. If you want to learn more, please take a look at our technical documentation available at Zebra Aurora Vision Developer Portal. You can find links to the sections of the documentation relevant to this tutorial in the video description below. Thank you for watching. For more information on Zebra Aurora Vision software products, visit us at aurora-vision.zebra.com. Alternatively, we can select all images and classify them with one click.